Hello, welcome back to Educator.com and welcome back to physical chemistry. So today we're going to continue our discussion of entropy, and we're going to talk about entropy as a function of temperature and volume. So let's jump right on in. So I have to give you a little bit of a warning for this particular lesson and the next lesson, and actually several of the ones that follow. There's going to be a lot of mathematics. Most of it is derivation. The mathematics in and of itself is really not difficult. It's mostly just taking derivatives and, equating one equation with another and seeing which coefficients are the same and identifying one thing with the other. The only thing that you have to worry about, the only thing that I'm really going to warn you about is there's going to be a lot of symbolism on the page. So it's really, really important to not lose the forest from the trees in things like this. At the end of these lessons, I will stop, I will recap, and I will tell you what is actually important as far as equations to remember and what you should really, really concentrate on. But just wanted to give you fair warning. There's going to be a lot of symbolism on the page, a lot of mathematics. So let's see what we can do with it. Nothing is altogether difficult, though. So, okay, now we defined entropy as follows. We said that, of course, that ds is equal to dq reversible over T. So this relates a change in entropy to an effect in the surroundings. To an effect in the surroundings, or the system. Again, it's just a question of perspective in the surroundings. Basically, the quantity of heat withdrawn from the surroundings divided by the temperature. That's it. That's all it is. The quantity of heat, say, withdrawn from the surroundings. That's it. It's just, it relates it to an effect in the surroundings. Now, can we use the equations we have so far? Can we use this equation and the equations we have so far from our previous work? This is the question. Can we use our equations to relate entropy to changes in the state variables of the system, which we can actually measure very easily? In other words, temperature, pressure, and volume. Temperature, pressure, and volume are easily measurable. Not that heat isn't. It's just that basically if I can find a way to use the equations that we have at our disposal to be able to express this delta S, or the ds, in terms of the pressure, the temperature, and the volume, and maybe energy, it would be very, very, very convenient. So that's what we're going to set out to do. That's our goal. That's our big picture. We want to express entropy in terms of temperature, pressure, and volume. Let's see what we can do. Now, we know that in a reversible transformation, so I'll just go ahead and put it over here. In a reversible transformation, remember from our discussion of energy, we said that the external pressure is actually equal to the pressure of the system. Because of something reversible, the system and the surroundings are always essentially in equilibrium. So the external pressure, we just set it equal to the internal pressure. So, therefore, our definition of work, because we're going to bring work back into this, definition of work, you remember the definition was P external times dV. Well, if P external equals P, then dW is just equal to P dV. Okay, so now let's go ahead and start with, again, our first law. First law expression, energy is equal to dQ, and in this case reversible, minus dW. Well, du equals dQ reversible. dW is just P dV. Okay. Well, we have this, ds equals dq reversible over t. So if I move the t over here, I get the dq reversible. I get that dq reversible is equal to t ds. So I'm just going to go ahead and put this into here, and I get the following. I get du is equal to, actually, you know what, let me, well, that's fine, it doesn't really matter. So du equals tds minus p dv. So I'm going to switch things around. I'm going to move this over here, and I'm going to put t ds is equal to du plus p dv. Now I'm going to divide by t, everything by t, in order to get ds alone. And I'm going to be left with ds is equal to 1 over t du plus p over t dv. This is a very, very, very important equation. This is called the fundamental equation of thermodynamics. So it's going to be the starting point for much of the work that we do subsequently. So this is the fundamental equation of thermodynamics. And it's nothing more than a combination of the first law of thermodynamics, which is an expression of, which is the definition of energy, and an expression of the second law of thermodynamics, which was just an expression of the definition of entropy. That's it. First law is energy, second law is entropy. We put those together and we come up with the fundamental equation of thermodynamics. So you don't need to memorize this because the derivation, as you see, is really, really very simple. That's it. Just put the definition of entropy in terms of the TDS into here and just manipulate it. That's it. It's very, very simple. So let me go ahead and actually go to the next page here and rewrite the equation again. So we have ds is equal to 1 over t du plus p over t dv. Okay, this expresses a change in entropy to changes in energy and volume. In other words, what this says is I can change the energy, I can change the volume, or I can change both. Either one of those or combined, that changes the entropy. In other words, I have two independent ways of changing the entropy. I can change the energy of the system, I can change the volume of the system. Either one of those changes that I make to the system will change the entropy of the system. That's all this equation says. That's it. So this expresses a change in entropy to changes in energy and volume, as well as the temperature and pressure. Notice I have T and I have P. Notice that every variable is represented. Notice that every variable is represented. Temperature, pressure, volume, energy, and entropy. S-U-T-P-V. It's all together. That's why it's called the fundamental equation of thermodynamics. Okay, some other things to notice. So, things to notice. Well, the first thing, the coefficients, the 1 over t and the p over t. Actually, I think I'll go ahead and do this in red. Why not? What the heck? So, things to notice. The coefficients 1 over t and p over t are positive. Very, very important. There are two independent ways of changing the entropy of a system. The first way is change the energy. That's that one. The other way is change the volume. If you make changes to either or both, you change the entropy of the system. Okay. Now, let's go ahead and, well, that's okay. I can go ahead and continue here. Got a little bit of room. Now, since 1 over t and p over t are positive, if I hold v constant, and if I change the energy, if I raise the energy, in other words, if the change in energy is positive, if this differential is positive, positive times positive is positive, the entropy is also the change in entropy is also positive. If I raise the energy of the system, the entropy of the system is raised. If I hold the energy constant, and if I raise the volume of the system, this is positive and this is positive, that means the entropy goes up. So, if I raise the energy of the system, I raise the entropy of the system. If I increase the volume of the system, I increase the entropy of the system, and vice versa. If I decrease the energy, I decrease the entropy. If I decrease the volume, I decrease the entropy.